be in here, and Dr. Rodekor has been teaching his classes this semester in here as well. So odds are, whatever your lecture, it should be in this room. How you doing today? Okay. Any questions? So before we get started, what'd you get? Sorry? I'm curious how you did that. Okay. 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 That is a great place to start today. So let's look at what we know and what we don't know. You're given, we walk 5 miles, so that is a displacement. We call that x1. That's the first leg of our journey. Then, after that point, we will move at a velocity of 3 miles per hour for a time of 2 hours. And we would like to know the total final distance, we call that sigma x, for this entire trip. So, we know we have walked a minimum of 5 miles. That is at least the bare minimum of distance walked. Then, separate from that, we move at this velocity for this time. So there's going to be a different distance piece there that we can add to the first one. So with these numbers and the formulas we've talked about, how far would someone walk if they moved at this speed for this amount of time? Not exactly. This is the first leg of the journey. This is unquestioned what we have done. And then after we did that, we're going to go even further at this speed for this time. So I would actually call this x2, and sigma x to be x1 plus x2. We went 5 miles, we're going to go even further based on this information. So x2 is going to be 6 miles. So the total distance traveled then should be 11 miles. How do you feel about that? Sorry? Oh, good news. We have several. So let's take a look. The next 3 on this page are all pretty similar. They all start factoring in acceleration. Good day.
Hey, sorry.
That is okay. Oh, yeah. Completely understand. I hope it went well. take a minute to breathe if you need it. Let me know if you have any questions. We just talked about number 15 on the assignment. You check the work that's on the board. Answer comes out to a total of 11 miles. So just go over that and make sure that makes sense for you. If it doesn't, let me know. Now I'm going to begin looking at 16 through 18 and how acceleration factors into those. So, go ahead and let you know. A lot of times when physicists write these questions, the problem will have a numerical answer that you can solve for. It just won't always make a ton of sense. For example, in number 16, a driver named Billy Bob is going to be driving, is stopped at a light. Then they're going to hit the gas and keep the gas pedal pressed for a total of 1.2 minutes. Does that ever happen in real life? When driving, do you ever put your foot to the floor for 1.2 minutes? No, typically not. So we're going to get numbers here. We'll get numbers that will mathematically be what the answer would be with what we're given. They just won't make a whole lot of physical sense. And that's going to come up a lot in some of these samples because human beings are writing these to generate the questions out of midair. I've written plenty of problems that have a solvable answer that just doesn't make any physical sense because when writing them, there's just some things that I forget to account for, and I apologize. It's going to come up, and I'll try to acknowledge it when it does. For this one, we're just going to get crazy big numbers that would not happen on an American road with a street legal car. So, in this specific situation, let's read the question, let's look at what we know, what we don't know, and then we will further define acceleration. Let's leave this in the corner for now. So, reading the question, Billy Bob was stopped at a red light, and that's the start of the experiment. So at the beginning of the experiment, we are stopped. So I'm going to interpret that as, in terms of our variables, Bob's initial velocity is 0. We know he begins the experiment stationary. We can pull that just from the words. Then the light will turn green, and Billy Bob is going to hit the gas and accelerate at a rate of 2 meters per second squared for a time of 1.2 minutes. I'm going to write that down, talk about what all that means. Oops. So, just to check, you both driven before? These cars? Okay. So, have we talked about the definition of acceleration? Okay, that is okay. Let us do that now. Come on, get your act together. There we go. So, these three things are the first three vectors covered in any physics class, and they're all intrinsically connected to each other. Displacement is the physical distance between 2 points. Velocity is distance displacement over time. It is how fast you are displacing. And acceleration is the change in velocity over time. So every new vector, we're taking the previous one and dividing it by time. So if you have a velocity, your displacement is changing every second. If you are accelerating, your velocity changes every single second. This should line up with, hopefully, what you can think about when you're driving a car. You hit the accelerator pedal, and your car's velocity changes. Your Speedometer goes from 0 to 60 in X number of seconds. Car commercials very frequently talk about, like, our model goes 0 to 60 in 3.5 seconds or something like that. And that gives you an idea of what the car's acceleration is. So, commercial says 0 to 60 in 3.5 seconds. That's a change in velocity, and it takes place over an amount of time. So you can figure out acceleration equals change in velocity over the time that takes. And it'll give you an idea of the amount of acceleration the car was under at that time. These units don't match up, so we would need to do a little bit of converting first to find a good answer, but it gives you an idea of where everything lives in the formula and how it applies to something that probably occurred regularly. So whenever you change velocity, you are accelerating. That includes speeding up and slowing down. In American English, the word decelerate gets thrown around a lot for when you're slowing down. But as far as standard international physics is concerned, the word accelerate itself refers to both speeding up and slowing down. Acceleration is any change in velocity. So let's use that and the formula given here, A equals delta V over delta T, to start looking at the improbable situation of Bob and his car. So, we are told the acceleration of this particular car, 2 meters per second squared. The unit of meters per second squared happens because in the formula for acceleration, we're dividing velocity by time, so we're dividing meters per second by seconds again, and that can simplify to meters per second squared. What that means is, every single second, this car will get 2 meters per second faster. So if I was to graph that as a quick visual, so, quick visual of velocity versus time. At time equals 0, we haven't moved yet. Velocity is 0, time is 0. After 1 second, we would have accelerated to a velocity of 2 meters per second. So after 1 second, we're now moving at a speed of 2 meters per second. 1 second later, we'll have sped up another 2 meters per second. Now we're at 4. Another second after that, speed up another 2 meters per second. Now we're at 6. As long as you're accelerating, your speed will keep increasing every single second you are in the state of accelerating. And we're going to be doing this for 1.2 whole minutes. So that's going to be quite a few seconds. How do you guys feel so far? Okay. Now, purple is visible from green. We've been told the initial acceleration, time, and we want velocity final. And the formula we were talking about, the definition of acceleration, A equals delta V over delta T, has all of those terms in it and will give us what we want. To help show that, I'm going to remind you guys of a mathematical principle. Delta anything represents final minus initial. So we want VF, We know VI, we know T, we know A. So we can start plugging in and performing some algebra. A equals 2, we want VF, VI equals 0, time's going to be a little bit funny here. We were given 1.2 minutes, while our acceleration is meters per second squared. Those don't match up. So what do you think is the easiest thing to do to rectify that? It's okay. By default, all the formulas we're going to use that involve time are designed standard to take seconds instead of any other unit of time. So this, meters per second squared, is the standard metric for acceleration. This is normal for physics. Meanwhile, to plug it into the formula, our formulas tend to be designed to take seconds, so we just need to figure out how many seconds are in 1.2 minutes. 1 minute equals 60 seconds. Do a little railroad trick. 1.2 times 60, if my memory serves, is 72. So if we don't plug in 1.2, we plug in 72, and I need to buy better markers. That's blue. So, what will be our grand total, or VF? How fast are we going after those 72 seconds have elapsed? Very good. 144 meters per second. Now, for the numbers we've been given for this particular question, that is correct. We have the correct answer. For a brief reality check about the improbability of this situation, you know what? I'm not very good at converting from meters per second to miles per hour in my head, so let me just pop that into a conversion program. 144 meters per second is the equivalent of 322 miles per hour. So, correct answer for the numbers. Not something that I hope could ever happen on a road. I'm pretty sure that beats the current land speed record of the fastest street legal production car at the moment. So I don't know who this guy is or where he got this car or how he isn't in turbo jail. I'd be curious to know those things. But so as far as the math is concerned, that is our answer to the first part of the question. So now we can look at the second part. When you get in a car and you hit the accelerator and you watch your speedometer go from 0 to 60 or what have you, do you stay still while that happens? No. While you're accelerating, you are still moving forwards. Because as soon as you go from 0 to anything, you start moving. So the whole time your velocity is changing, and the whole time you are already displacing. So in that 1.2 minutes, Bob is going to travel somewhere while that is happening. And that is the next thing we were asked. We would like to know delta x. Now, is the formula we just used going to tell us that piece of information? Formula we just used will help us find delta x? That's okay, sorry, not trying to trick you. So this just doesn't have delta x in it, so this is no longer the formula we want to be using. Which means it's time to go back to that list of 4 wonderful, possibly even fantastic formulas that you'll see the rest of your physics class career. Of these 4 that will come up repeatedly, the first one is the definition of velocity, the second one is the definition of acceleration, and the next 2 start combining those 2 principles together to accomplish some specific things. Formula 3, out of all of these, is probably the most important one because it's the most versatile. So Formula 3 is like, it's the middle child that takes the most initiative and gets the most accomplished. This is the type A formula. This is the definition of velocity. This is the definition of acceleration. Formula 3 is specifically looking at displacement while you are accelerating. So if we look at the formula itself, we have delta x equals velocity initial times time plus 1/2 at squared. Just a brief note, between the way that I write things on the board and the way that the way that the slides and previous authors might have written the slides, V0 is the same as VI. They all mean starting velocity. The 0 subscript refers to velocity at time of 0. I might occasionally call it V0. That's N-A-U-G-H-T, because one of my professors is South African, and naught is just a common term there for 0 or nil. So the 0 here means it's just the initial velocity. I've got it written over there as VI. It'll mean the same thing, and I'm just going to swap back and forth between the 2. Please call me on that if that is ever confusing. But this formula is nice because it can take into account, like as we are tracking our displacement, it can take into account whether we are accelerating or not. The first formula, just the V equals delta x over delta t, doesn't factor in acceleration at all. You can put a big asterisk and footnote next to this first formula here saying this is only for constant, non-changing velocity when you are not accelerating. Formula 1 can't handle any acceleration at all. You have to be moving at constant velocity for this one to work. But for this one, we can have a displacement of velocity and an acceleration all over some amount of time. And what's really neat about this formula is, if you weren't accelerating, if you were moving at constant velocity, if A was 0, this whole term would go away. We'd have delta x equals v times t. That's the same as the first one. So this is Formula 1, but more accurate, more useful in more situations. So this will be the one that comes up the most. And it'll be the one that will help us in this particular situation because we want to know how far we moved while we were accelerating for that 1.2 minutes. So, that's the one we're going to use for 16 part B. How far did the travel? We have delta x equals v initial times time plus 1/2 at squared. Delta x is what we want. Our v initial was 0. We started from a standstill, so this whole term is ultimately just going to go away. Doesn't really matter what time it is if the thing you're multiplying it by is 0. So that's just going to simplify out. And leave with excuse me. Sorry, guys. That's a sign that I've been talking too much. I'm going to get some water. Please take this as a break from the sound of my voice. Pardon me. less choking now. 1/2 times our acceleration of 2. I'm going to take time and then square it. We're going to use the 72 seconds again. All of our formulas want seconds. And that will give us a very large number for delta x. Don't remember that large number. Check real quick. Thanks. Correct. And that is in units of meters. So, very big number, very many meters. That is the correct answer. And excuse me. Real quick. Because I don't have that on the top of my head. 5,184 meters is the same as 3.22 miles. This person drove 3.22 miles in 1.2 minutes. Not even at top speed the whole time. I don't know what machine this guy has, but I want one, and I want no one else to have one. But mathematically, these are our correct answers. Physics problems won't always match reality, and that is everything we need for number 16. 17 and 18 will be very similar, except there's going to be an additional formula that we now have to take into consideration. Any questions about 16? We can do 17 together with the new formula. Okay? 17. Did I step on the board again? Okay, so in 17, I'm assuming this is the same Billy Bob, similarly breaking most laws of reality and the road. In this version, Bob is cruising down the road at 36 meters per second. So at the start of the question, our initial velocity is 36. And at this point, Bob somehow sees 1.2 kilometers away a stop sign. Stop sign? Stop light. And Bob is going to hit the brakes and begin decelerating, slowing down, as Bob travels that 1.2 kilometers. So delta x is going to be that 1.2. We're going to move 1.2 forwards as we are slowing down. And since we are slowing down to a complete stop, our final velocity will be 0 meters per second. So, when driving, whenever you've noticed there's a red light ahead and you hit the brakes, you always have to slide some distance forward as you're slowing down. It's never instantaneous. You're never going to hit the brakes, come to a complete stop, and lose all of your velocity. You wouldn't want that to happen because you throw your neck out, among other things. You always have to slide. There's always a distance involved while accelerating or decelerating. It's never instantaneous. And it's the same in this case. We are asked for part A of 17, what is Bob's acceleration in this unique situation? And just at this particular time, without looking at part B, without working ahead, ignoring this for a second, with just what we've been presented and just what we want, looking at the three formulas we have used up until this point, will any of them give us A with what we have? Okay, good. The one that we haven't used yet. So 17A, we're not given time at all. We have no time. All these formulas have time in it. They're out. 4 doesn't have time in it. This is the odd man out of this group of 4 formulas in that it doesn't have a time term in it. And it's also the one that is just used the least. It's hands down kind of the weirdest one, the one that you forget exists until you need it. But it'll be on all your formula sheets, so it won't be hidden from you. And it's useful in this situation because it correlates distance, velocity, and acceleration without needing to know time, which is exactly what we need right now. So, using formula 3, Vf squared, 0 squared equals V initial squared, that's 36 squared, plus 2 times A, which is our unknown, times D, that's 1.2 kilometers. So all of our formulas will be designed to accept seconds and meters per distance. So how many meters is 1.2 kilometers?
1,200.
Very good. And now we just have to use some algebra to find A. Let's simplify this online. I don't actually remember what 36 squared is.
1296.
Thank you. And that'll be plus, let's simplify that to 2,400 times A. What kind of A are we going to get from this? Nice. And what are the units of acceleration? Missing one teeny last second. Very good, square. All right, negative, and that is on purpose, that is correct, negative 0.54 meters per second squared. The negative means we are slowing down. If positive is the forward direction, and we are slowing down, that means we are accelerating backwards. If you think about positive and negative as a continuous plane, we are driving forwards, but since we are slowing down, our velocity becomes more and more negative, more and more towards 0 in the negative direction the entire time. So you can be moving forwards while accelerating backwards. You do it every time you hit the brakes. So negative acceleration means slowing down, can mean accelerating in reverse. Hitting the brakes, you'll never turn around, but sometimes in movies you might see someone, instead of hitting the brakes, just slam the car straight into reverse, hit the gas, and by doing that, they stop going forwards and start going backwards. That would be the same thing as this situation, but you kept accelerating backwards after coming to a complete stop. Realistically, this acceleration would cease once you hit 0 if you were using the brakes. If you were using reverse, you keep accelerating backwards. I apologize, I might have made things more complicated than it needed to be. But that is this car's acceleration as it slows down. The negative is good, negative makes sense. The last thing 17 asks us for is how much time did this whole thing take? So we want t, we know all of these things. Which formula would be the easiest way to get to our answer? Yep. We know the acceleration now. We know our change in velocity. We want time. This is the simplest way to do that. We could use formula 3 to get there, but then we invite ourselves into having to work quadratic. Let's just avoid that if we can. And since we got a negative acceleration, signs and where we put them are going to matter in how we do this one. Delta V, terribly sorry, is always final minus initial. Our final is 0. Our initial isn't. So we're going to do 0 minus 36, and that'll help us make sure we get the time that we want. I recommend multiplying both sides by delta t. And simplify the right side to just negative 36. T equals negative 36 over negative 0.54, which should give us some slightly larger positive answer.
66.6.
Thank you very much. So this whole thing took just a little longer than a minute, which is spooky. How do you guys feel so far? Number 18 works very similarly to the previous ones. I'd say the main thing that's different about 18 is that neither your initial or final velocity are going to be 0. That's the only real difference. I'd like to instead take a minute to start looking at what you're going to need when we do 19, 20, 21. Because those all involve falling and projectile motion, as opposed to simply moving in straight lines. So, sorry, I have one. Here we go. Brief timeline update. I'm still thinking the homework will be due on the 16th, but I'm thinking we might end up finishing it in class together, just so that we can make sure we go over all of the individual cases for all the remaining questions. Specifically, these last 3 are similar, but rather involved situations that are going to involve looking at an object moving in more than one axis at once. I want to make sure that I work with you guys to understand exactly how these problems work, because they're going to be all on the next test, on the final, and all over Physics 1500. So I want to take time to go over those with you guys. So I want to start it today to give you the tools to at least be thinking about it and starting to work on it. We'll spend Friday finishing the assignment, and I'll take it up by the end. And I will let you know with regards to collecting it and grades and what will happen the next week or 2 for the next test. The timeline might be being pushed around a little bit, but I'd rather delay things than force you guys to do projectile motion by yourselves.
Is our test next week, or?
My original plan was to make it this Friday, because Honors Day is this Wednesday, which is not going to have class. So reminder announcement, no class on the 21st. It's Honors Day. It's simpler that way. People have things going on. We will meet Friday that week. I might move the test away from that day, just so that I can give the homework back and we can review. So that might put the test here. If that happens, I'd have it graded for you by the 30th, and we would spend the rest of the 30th and our last meeting, Wednesday, May 5th, preparing for the exam. If that ends up being the case. Any issues? Any questions?